times partial x of the inside function, which is x squared plus y. Yeah, it is 2x, but I got to write out my work. Indeed, this is work that I hope to soon stop writing. Certainly by the time you leave this course, I hope that you don't need to write all these intermediate steps. That's true. But for now, we're learning, so let's try to take it as slow as I can. So this is 2x, and that's constant, so it's 0. I'm using the additivity and the homogeneity of the partial derivative, which was in the theorem we haven't proved. We haven't proved those yet, but the proof of those will not be terribly shocking. It's basically just going to be everything about partial derivative. I mean, look at the definition of the partial derivative. It's made in terms of the ordinary derivative, right? So all of the properties for ordinary differentiation kind of transfer over, since the partial derivative is just defined by an ordinary derivative holding one of the other variables fixed. Simple as that. Here, let me do an example which will be more troublesome to you. Partial x of x to the y. Partial y of x to the y. Yeah.
For the partial x of x to the y, that's treating the y as a constant.
Y is a constant, right?
And for the other one, you're treating the x as a constant.
Right. True. So the top one, right, it's like d dx of x to the n, right? This one is like d dx of a to the x, right? Or perhaps it would be more appropriate to say d dy of a to the y, yeah? So with that identification, this is y x to the y minus 1, whereas this one is the natural log of x times x to the y, because that's the derivative of the exponential function. You see, the first one's a power function. The second one is an exponential function. An exponential function has constant base. A power function has constant exponent. Yeah?
Why is it not 0 to the second one if it's dx or partial of x partial of y?
I'm sorry?
The second part of the last example, then you have a partial of.
It's just,
Are you just saying it's like a constant a to the y, not x to the y?
I'm saying the pattern is like it's like differentiating with respect to y a to the y.
It didn't say that the properties of partial x and partial
she was misreading it.
Oh, okay. I'm not discounting your question, but I don't understand it yet.
Isn't the properties of partial x and partial y 0?
It is, but what does that have to do with this?
Isn't that just partial x and partial y?
No, this is partial y of x to the y. It is not the same. Here, let's look at some more. How about partial x of xy squared plus, I don't know, inverse tangent of xy? Well, I can do the first part easy, right? That's just y squared. And then plus what? Plus 1 over 1 plus xy squared, because that's the derivative of inverse tangent. And then I have to do partial derivative with respect to x of xy. What's the partial derivative of xy with respect to x? I know, it's okay. There is something about these expressions that messes people's brains up. I don't know what it is, but these are more insidious. They should be simpler, right? Because they're just basic derivatives we've done before, but there's something about the pattern of the symbols here which is vexing to people, which is why I went over it. So I don't know why, but it's just... So this is what? It's just y, right? And I can either write xy squared or x squared y squared. There you go. It's fun, no? Partial y of y sine of y e to the y. You can ask me why. Oh, why did I just have y? It's all y's. That's no fun. X. There. Is that better? I can make it x to the 42. There you go. So that pulls out because it's a constant, right? And then I have partial derivative with respect to y of sine of y e to the y, because the constant pulls out. And then this is cosine of y e to the y. And then I have to differentiate what? This product. And when we see products, we use the product rule, right? I guess I should have put an x dependence in the argument for the exponential to make this properly awful. I mean, it's not too bad, but so this gives me e to the y plus y e to the y. I personally don't think this is hard. Am I right? Yeah, we're just doing derivatives. This is why I actually require this of physics students when I teach physics, even though it doesn't have a calculus 3 prerequisite. I spend 10 minutes to teach them this. Sans all the interpretation and concept, just as an algorithm, something you can do. And then you can usually do it. I mean, you could teach a middle schooler how to do this in like 20 minutes or something, right? Maybe you got some candy for them. I don't know, whatever it is. Or that's not what they want. Well, that's not how I was thinking of it, but well, that's unpleasant. Okay, so getting back to the directional derivative story, right? I haven't actually calculated a directional derivative yet. I should do that. So the little theorem we have is just this. The directional derivative in the u hat direction of f at the point P is equal to u hat dot partial f partial x at the point P, comma partial f partial y at the point P. Now, this thing is so important it gets a name. This is called the gradient of f at the point P. Or, as I'm fond of denoting it, nabla f at the point P. We'll be spending a few hours in here studying the gradient. It's far more interesting than just the directional derivative. That's just the start of the story. So, but, this is nice, right? Because there's no limit anymore. We just calculate these partial derivatives. As you can see, you can do without actually taking limits and piece it together. So, for example, if we have f of x comma y equal to x cubed plus xy squared, and I want to find rate of change of f of xy at some point, let's say 2, 3, in the u hat direction. So I'll let u hat equal ab. I'm going to keep it arbitrary here to get the most out of this example, though. What do? I calculate the gradient of f. is nabla f, which is partial f partial x, comma partial f partial y. See, this vector of rates of change really describes the total change in the function. This is the thing which is analogous to the slope. But anyway, in some sense. So this is 3x squared. Oh, I'm sorry, plus what? See if you agree with me. If you differentiate that with respect to x holding y fixed, what do you get? Do you agree with me? 3x squared plus y squared. How about the y derivative? What would you get? Okay, 2xy, yeah. Now, to calculate the directional derivative at that specific point, I must evaluate at the point. Just like when you find a tangent line to a space curve, you're supposed to plug in the point of tangency into the velocity. Ah! Ah! You guys, so many of you. Oh. Whatever. I have expressed my dismay. I'm sure you'll fix it by the next test. All right, so let's see here. 3 times, that's 12 plus 9. And 2 times what? 2 times 6. I mean, this vector is 21, 12, if I did it right. And then so we can calculate the directional derivative in the u hat direction of the point of the function f at 2, 3 is equal to ab dotted with this vector, 21, 12. What's that give me? That gives me 21a plus what? 12b. That's the rate of change of this function in the ab direction. I'm assuming what about ab, though? They exist. True, but they're also subject to this condition here. They have unit length, right? So, can you guys tell me what's the maximum rate of change? What's the minimum rate of change? Yeah? Nope. Good guess, though. If you put u hat equal to 2112 divided by the square root of 21 squared plus 12 squared, what would that mean about the unit vector u hat geometrically as it relates to the gradient vector? Same direction, right? Look, it's defined in terms of a dot product, right? So the biggest this can be is when these vectors are parallel. So when these are parallel, the value of the gradient is simply the value of the directional derivative is simply the magnitude of the gradient. In fact, this thing I wrote in the denominator, that is the maximum rate of change, which is actually achieved when u hat lines up with the gradient vector. The negative of this is the maximum, the maximum decrease possible at the point, and that'd be in the opposite direction. And then you can get anywhere in between those, from 0 all the way to the other. It means it goes 0, just make the u hat perpendicular to the gradient vector. Oh well, if you didn't understand what I just said, it's okay. I'm going to do this again, at least one more time. Hopefully it will sink in next time. If it didn't sink in this time, I think we have to go. Okay.